Welcome back, everyone, to MAT1841. So last time we discussed the frequency moment sketching and gave a idealized version of the F0 sketch for the count distinct, so the number of distinct elements in a stream. And we also gave a non-idealized constant order approximation. So we gave a 6 approximation, which isn't so great, but we showed that we can get a 6 approximation with a good probability. And it turns out that, well, we learned how to improve the failure probability, or how to decrease the failure probability by using medians, but we didn't really learn how to decrease the epsilon error, approximation error. And so that's what we're going to do today, but it requires a little bit more machinery. And so I'm going to first start by presenting another version, another non-idealized version of a constant approximation that's going to lend itself a little bit better to what we're about to do. So let's go ahead and get started. So let's call this the another non-idealized Flageolet-Martin sketch. Counting. And there are a number of different ways of doing this. The one we're going to show today is going to highlight something called geometric sampling. And that's going to be a technique that we're going to make use of in the full version of what we're doing. So this is 1985. Okay, so what are the steps? First, we're going to start as usual. Pick H from a 2-wise family. By 2-wise, I just mean 2-wise independent. Family from, let's say, from n to n. For n a power of 2. And we'll round up if necessary. So basically, we're going to be working in powers of 2 today. Computer scientists really like powers of 2. And then the next thing we're going to do, and this is sort of hinted by our sort of sketching overview that we did back when I was using all the PowerPoints, we're going to maintain x, which is going to be equal to the max over I in our stream, or AI in our stream, however you want to call it. And we're going to say that the LSB of H of AI, where LSB is the least significant 1-bit. And 1-bit of a number. So for example, just to make it concrete, LSB of 1011011100 is going to equal 3 because we have a 1-bit in that position. And LSB of 10110000 is going to be 1, 2, 3, 4, 5. It's going to equal to 5 since we have a 1-bit in that position. Okay. So this is the same thing that we were doing with the log-log counting. And what we're going to do is we're going to take the maximum of these numbers. So effectively, it's the same as taking the minimum if you think about this as a number between 0 and 1, and you're taking a like order of magnitude. So that's all we're doing. And then we're going to output a guess. Output the guess, let's call it d tilde is equal to 2 to the x. Okay, so that's going to be our guess after we keep this maximum 1-bit. And this guess is going to be a reasonably good estimate of the cardinality, like the one we had last time. And then we're going to show how to refine it. So first, well, for fixed j, so we're going to fix j everywhere. We're going to let Zj be equal to the set of all bi's, where remember the bi's are the distinct elements. So the ai's are all the elements of the stream. The bi's are the distinct elements after you've removed duplicates. So set of bi in the stream. Oh, I am sorry. I don't know. I'm getting phone calls right now. Yep. So bi in the stream such that the least significant bit of the hash of bi is equal to j. Okay, so Zj is just going to be all of the number of times that the least significant bit of a hash function was equal to j. And let's go ahead and define another useful quantity. So Z greater than j is going to be least set, well, as you can probably expect. I should make a note of these are unique elements. Unique elements. Let's say this is unique of A1 through A whatever. What symbol was I using for the total number of elements in the sketch? I forget, but A1 through whatever's. Okay, and then what we're going to do, let's the significant bit h of bi is greater than j. Okay, so all we're doing is we're counting the number of things that are in our stream, number of unique items in our stream that have a least significant bit of a particular value, or greater than a particular value. And well, we really like indicator variables. Let's define yi to be equal to 1 if the least significant bit of h of bi is equal to j, and 0 otherwise. So, well, what's the expectation of yi? How often is the least significant bit of a randomly uniform number going to be, say, 5? Yeah, so it's going to be 1 over 2 to the j plus 1. Okay, so basically because you're basically flipping a bunch of coins and they're asking, are they all coming up tails? Okay, and well, we can also compute the variance. So the variance of yi is going to be the expectation of yi squared minus, well, the expectation of yi squared. And of course, it's an indicator variable, so yi squared is just yi. So that's going to be 1 over 2 to the j plus 1 minus 1 over 2 to the 2j plus 2, which is of course less than 1 over 2 to the j plus 1. Okay, so we really like bounding variances because that allows us to use various concentration inequalities, like Chebyshev and so on. Okay, so now what we're going to do is, well, Glenn, we know that Zj is just the sum over all of our bi in our stream of these indicator variables, yi. So this way we're actually going to be able to estimate these random variables. And so then the expected value of Zj is going to be equal to d over 2 to the j plus 1, where d is equal to the number of unique elements in the stream. So number of distinct elements. And furthermore, we can also estimate Z the expectation of that greater than j, which is just going to be equal to d times 1 over 2 to the j plus 2 plus 1 over 2 to the j plus 3 plus dot dot dot. And what's that equal to? Geometric series. So yeah, it's also going to be d over 2 to the j plus 1. Assuming you go on to infinity, but certainly it's bounded by that, which is what we care about. Okay, so now what we have is now we have a sense of how many things are going to fall into each of these Zj's, right? And what we can next, well, what's the variance of Zj? Well, the variance of Zj is just the variance of the sum over all our yi's, which is equal to the expectation of the sum over our yi's squared minus the expectation of the sum over our yi's squared the other way. And notice that if we expand this out, the expectation of y1 plus dot 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 plus yd times y1 dot 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 plus dot 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 yd. If we expand that out, that is just equal to the expectation that y1 squared plus dot 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 plus yd squared plus 2 times the sum over yi, yj for, I1 not equal to I2. Let's make that I because j is already a taken variable. Why is this true? Why can we say less? What fact are we using about our random variables?
You take expression once you do that. It's just expansion, right?
But we have to be a little bit careful. So in the next step, what we're going to do is we're going to use 2 independents. Sorry, we haven't used it yet. So by 2 independents, we know that the expectation of yi Yeah, I haven't actually done that step yet. Y1 times, actually, no, I have used this here in order to like combine together the different indices. So expectation of yi2 is going to be equal to the expectation of yi1, yi2. So that's going to be, did that make sense?
I don't see why would, isn't now we just expanded it, we just squared it.
Yeah, so the issue is that basically when we're doing this expectation, we are allowed to do this thing by two independents. And so then depending on where exactly you're doing your expansion, whenever you do your expansion, you do need to use two independents in order for this to be true. Yeah. And so once we do that, let's allow, which is why we need a two independent hash function to begin with. So let's suggest the sum over expectation of yi squared minus the expectation of yi squared, which is equal to the sum over the variance of yi, which is less than d over 2 to the j plus 1, which implies that the variance of zj is less than d over 2 to the j plus 1. Okay, now the next thing we're going to do is now for j star equal to, let's call it the floor of log of d minus 5. We have that, well, clearly, when log of d minus 6 is less than or equal to j star is less than or equal to log of d minus 5. Plus, we also know that the expectation of z sub j star, so for this particular value of j star, that expectation is going to be, because of this part, that expectation is going to be less than or equal to d over 2 to the log d minus 5. And it's going to be greater than or equal to, because of the right-hand side, d over 2 to the log d minus 4. Okay, so all we're doing is we're plugging in our value of j star. And so now we have a bound on the expectation of z sub j star. Let me make that jar star not too far up. J star. Well, what are these two values? So can we simplify this at all?
D minus 5, right? I assume LG is base 2 log.
Yes, yeah, so this is base 2 log, yeah. So what you're going to have is greater than or equal to 16 and less than or equal to 32. Okay, everyone, yeah, so we're just making use of base 2 log here. And so this gives us a tight bound on what the expectation of z sub j star is. And now what we can do is you can say that the probability that z sub j star is equal to 0. But of course, that's less than or equal to the probability that z sub j star minus the expectation of z sub j star is greater than or equal to 16. So we're using the same trick we did last time. The probability that's equal to 0 is clearly, well, less than or equal to the probability that it deviates by at least that much from its expectation. And so this is less than or equal to the variance of z sub j star over 256. In here, 256, which is less than 2 to the d over log d, d over 2 to the log d minus 5 over 256, which is equal to 1/8. And well, this is of course by Chebyshev, which we've been using over and over again. So we get, so this is some good probability that things don't fail too badly. So it's the same sort of strategy that we did at the end of the class last time. And so therefore, we know that for j equal to log, so now we're choosing a different j. Instead of j star, we're choosing a different j that's log d plus 5. We can use the same sort of logic. We have that j is greater than log d plus 4. And so therefore the expectation of z sub j, greater than j, is less than or equal to d over 2 to the log d plus 5, which is equal to 1 over 32, which implies that the probability that z sub greater than j is greater than or equal to 1 is less than or equal to, is less than 1 over 32 by Markov. because we know this is a whole number. And so basically what we're saying is that we know something about the expectation, and therefore in order to deviate sufficiently much, we can just use this weaker inequality of Markov to say that the probability that we have something that's over J, the probability that there is some object in our original stream that when hashed has the least significant bit at J. For this J that's significantly bigger than log D is well less than 1/32. And so what we're doing is we're bounding on both sides. So less with probability 1 minus 1/8 minus 1/32, the maximum least significant bit will be between J and J star, or J star and J, to go from smaller to higher in a constant range. What does this mean? This means we get a O of 1 approximation. So we get a constant order approximation with high probability. And I think this, if I remember correctly, this is a 64 approximation. Some power of 2. Because basically what we're saying is that with high probability, the maximum number of bits that are, well, the largest number of the least significant bit is going to be pretty close to log D, as you'd expect. So in expectation, you'd expect it to be somewhere around log D, and it's not going to be more than 5 off in either direction. Or 5 off, 6 off. I forget, this might be a 32 approximation. It doesn't really matter. So then what we can say is, well, our estimate, D tilde satisfies D over C is less than or equal to D tilde less than or equal to CD for some constant C. With probability 1 minus 8 over C using O of log. So we can actually adjust a little bit the probabilities just by messing with how many bits we're allowing on either side. So that's what we're saying here, using O of log n bits of space for the max least significant bit, and O of log n space bits for the hash function. Because remember, we still also have to communicate the hash function, and our construction of that required making use of elements of this finite field, which we have to store. Okay, so it doesn't look like we're much further than we were last time, right? Because this is still an O of log n solution, even though it's slightly better because for each of our max least significant bits, we only need log n bits, but still it's not that much better. So what we're going to do now is we're going to show a clever way of refining this to a 1 plus epsilon solution. So refine using the sort of geometric sampling trick, 1 plus epsilon's solution, using geometric sampling, which we couldn't do for, based on the last solution we did at the end of class last time. So what are we going to do? Well, let's first start with something super duper simple. Let's give a trivial solution that only sometimes works. The trivial solution, TS, stores the first C over epsilon squared distinct elements for some constant C. So when is TS a 1 plus epsilon solution? So sometimes this solution will be really good. So if you store the first C over the E epsilon squared distinct element, then sometimes this will be a really good answer. So I am feeding you a list, and you have a limited memory bank of C over epsilon squared. So you just store the first C over epsilon squared things. Yeah, exactly. So this trivial, well, I did call it a trivial solution. So this trivial solution happens to be a 1 plus epsilon solution. In fact, it's a 1 solution because it's exactly right. So it is a 1 plus epsilon solution. If, well, D is less than or equal to C over epsilon squared. But now, normally, we can't really assume that's going to be less than or equal to C over epsilon squared, right? But what we can do is, remember with this geometric sampling, we just analyzed how many things have a least significant bit in each particular position, right? And each of those varied by a factor of 2. And so what if we just store a bunch of these trivial solutions and actually store the number of elements in each of those that had a particular least significant bit? Then what would happen is you'd probably end up with one that was reasonably close to C over epsilon squared. And then you could scale that up. And that's the sort of intuition for what we're about to do. So this is a somewhat more complicated algorithm that makes use of the geometric sampling idea that we just did. So first, we're going to instantiate TS0 through TS log n. Okay, because of course we only have log n bits that we need in order to store these things. Roughly speaking, there is of course some chance that you need more than TS log n bits because you might have some thing that has just a bunch of zeros before the first significant bit, but that doesn't really matter because the probability is really low. And of course you could double this and you still would be the same asymptotically. So let's start with this. And then what we're going to do is we're going to pick, well, actually it's not even going to be possible because we're going to pick from a family that only maps from n to n. So everything's going to have at most log n bits before the first significant bit. So we're going to pick from a 2i's family. And the next thing we're going to do is we're going to feed each AI to TS sub least significant bit of G of A sub I. And we're going to output Bj times 2 to the j plus 1, where Bj is equal to, well, TSJ, which is the TSJ, which is approximately 1 over epsilon squared. And I'll make some of these quantities a bit more precise later. So what are we doing? Basically, we have this TS0, we have TS1, TS2, and so on, all the way to TSJ, all the way to TS log n, right? And what's going to happen is, well, we're going to fill up these things. And this size is going to be approximately C over epsilon squared. So we're going to fill that one up. And the next one we're probably also going to fill up. So these are completely full. And so these are not particularly useful. But each of these, the number of things that get mapped to them decreases by 1/2 each time, right? So eventually, what's going to happen is around TSJ, you're going to have it's not going to be completely full anymore. And of course, the one before it might also not have been completely full, but had about twice as many. And then at the very end, this is probably empty, but maybe you have something there. And so what's going to happen is we're going to use this as an estimator, and then scale it up because we assume that on average, a fraction 1 over 2 to the j plus 1 fraction is going to get mapped to it. And so therefore, if we scale that, the number of things, the proportion of items there up by 2 to the j plus 1, you're going to get an even better estimator for the actual number of distinct elements. Okay, everyone following? That's the overall intuition. But of course, we need to be a bit more precise about what we're doing. So, well, let the random variable Bj, which we just defined, be the number of distinct elements hashed by G to TSJ. Okay, and well, let's let the expectation of Bj be equal to D over 2 to the j plus 1, which is equal to, let's call that Qj. Okay, and because we already did this analysis in the previous section, I'm going to be a little bit hand-wavy with my analysis here and just use big O notation. So note that by Chebyshev, Bj is equal to Qj plus or minus something on the order of root Qj with good probability. Okay, and this is basically just taking advantage of the fact that we already did this analysis carefully in the previous segment. And here we're just going to use big O notation to hide all that. You could also take the time to carefully work through all the constants here, but we're not going to. And now this here is equal to 1 plus or minus O of epsilon Qj, if of course Qj is approximately equal to 1 over epsilon squared. because that was by construction. We picked the j so that qj is approximately equal to 1 over epsilon squared. So that's roughly its order of magnitude. And so note that 1 plus or minus O of the square root of qj over qj times qj, well, that's going to be exactly what we want. So that's O of 1 over epsilon over 1 over epsilon squared is equal to O of epsilon, which is how we got that term. Okay, and then we notice that the bj's decrease by factors of 2, roughly speaking, and with good probability, one of the qj's is close to 1 over epsilon squared. Another thing we can do is, so in practice, this isn't quite what you do. In practice, what you do is here, more precisely, we use j equal to the ceiling of the log of epsilon squared d hat over 32, where d hat is a constant approximation. Okay, so what we're doing there is we're making use of the fact that we already have a constant order approximation, whether that's 64 or 6, as in what we got yesterday. We have a rough idea of which of these bj's we need to, which of these trivial solutions we need to be looking at. And so we already roughly know which trivial solution to look at based on this analysis. Okay, and so that means that, well, one of these is close to 1 over epsilon squared. You actually don't even need to necessarily store all of them because you roughly know which ones you're looking at. But for now, for ease of analysis, we're going to store all of them. Well, they decrease by factors of 1 over epsilon squared. And well, this gives us, it turns out that this gives us the estimate that we want in a final amount of space. So the final space that this requires is c over epsilon squared times log n times log n times log of 1 over delta. Where do each of these pieces come from? Well, this here is just the number of unique that we're storing in each of these, each of these trivial solutions. And this here is the cost of storing the entries and hash function. Because of course you do need to store each of these entries, and that takes up the log n, all the hash values. And this here is the copies of the trivial solution, which you may not need all of, but for our easy analysis, we're just going to assume that you need all of them. And this here, what is this? What is this 1 over delta factor that we're adding in? Where did that appear last time when we were doing the idealized analysis? So this factor actually appears because when you're doing this analysis, I said that things work with some good probability, right? But how good of a probability? Like the good probability might be 1 minus, like might be 2/3. And if we want to have a even better probability, say 1 minus delta, well then you need to do something like the median trick to lower the failure probability. And you need to do that trick precisely log of 1 over delta times. So this is something like medians to obtain high success probability. In something like a constant factor approximation. But this is just to obtain high success probability, because there is some chance that things will go completely wrong and you'll have the maximum bits are set way far in the distance. And so this is just accounting for that probability. And so this ends up being O of epsilon squared log squared n times log of 1 over delta bits. Okay, and you can do better. This is not a tight analysis. You can do much better. E.g., this algorithm I described last time, or last week, epsilon squared log n plus log n, where this is just for the hash function. And in practice, it's really just log n bits. So this is for hyperlog. And it turns out even that isn't optimal. So if you look at the paper from King, Nelson, and Woodruff in 2010 and pods. What they got is that's actually, you only really need O of 1 over epsilon squared plus log n bits, which is optimal. And you can do that. But that requires much more sophisticated techniques as well as a lot more careful analysis. So like we sort of played fast and loose with our constants and let things just that we didn't really care about. And with a lot more careful analysis, you can get significantly better space complexity. Though in practice, everyone just uses hyperlog since that's good enough. The difference between log and constant in practice is, well, very, very small. Does anyone have any questions on that before we move on? Okay, so what have we done? We have now shown that you can actually extend these ideas from the idealized setting into this, from the idealized hash function setting into these settings of actual hash functions we can construct. It does take more work, but you can use the similar types of methods, including things like averaging or medians in order to power up your analysis, basically. So the next thing we're going to do is, I think someone asked last week when we talked about hash functions, do you ever actually need more than strongly universal? And so far, we haven't seen any examples of that, right? Because all the hash functions we've been using have only been 2 independent. It turns out that for at least the F2 sketch that we're going to do, it's going to need more independence than that. And so we're actually going to see why it's important that we are able to construct these k independent hash functions and not just 2 independents. So let's go back to the F2. So this is the second moment frequency sketch. And we'll see that we need a higher amount of independence. So again, we're going to consider a stream. So same notation as always. S is A1 through AN. AIs are from some set M. So note that I will sometimes index from 1 to M and sometimes from 0 to M minus 1. If it's ever unclear, just tell me. But in my mind, they're basically equivalent because it's either 0 or M. So. And then, of course, we're going to let Fs be the frequency. So same notation as last time. AI such that AI is equal to S. And this is going to be the number, the frequency of S in the stream. And we want to estimate F2 now, which is equal to the sum from S equal 1 to M of F sub S squared. And the way we're going to do this is we're going to make use of something that's similar to a random projection algorithm, if those are things that you've seen before. The way this will work is we'll first start by choosing a random hash function. So let's let H be from S to, and we're going to map this actually to the set -1, 1. Okay, so this is going to be, we're mapping into a slightly different set. It's going to effectively be a Bernoulli random variable, except that instead of being 0, 1, it's going to be -1, 1. And we're going to let this be 4-wise independent. And we'll see why we need the 4 later. Okay, so these are 4-wise independent, which means that if you map 4 different things, you can treat them as if they're all -1, 1 random variables.
What is S here? Do we fix S?
Oh, sorry. Let's call, this is the alphabet. What did I call that? Did I call that anything? Maybe I meant that to be from M. No, I did not mean for that to be from. Let's leave it as S for a moment. It'll become a little bit more clear when I get a little bit further down. So basically the set of possible items there. So actually, I think that is M. Yeah. Okay, so we're going from M to -1, 1. The next thing we're going to do is we're going to let X sub S be equal to the hash of S. So a Bernoulli random variable with equal probability of going to -1 or 1. And then what are we going to output? Well, we're going to output A is equal to the sum from I equal 1 to n of h of ai squared. So what does this mean in practice? So this is some formula that's not actually a procedure. So what we're going to do is each time we see s, we're going to add x sub s. And note that x sub s is either -1 or 1. So each time we see that, we're going to add x sub s to a variable. And we're going to square at the end. And notice that A is also equal to the sum from I equal 1 to m of x sub s, f sub s squared. Okay, because each time we see, say that 5 maps to 1. So each time we see 5, we're going to add 1 to it. So it's equivalent to saying that, well, how many times did you see 5? Well, you saw it twice. And so we're going to add that in this version. And if it happened to be that 6 maps to -1, and every time you see 6, you add -1 to it instead of 1. And what is our claim? Our claim is that the expectation of a squared is less than or equal to 3 times the expectation of a squared. And this isn't going to be tight, but it's going to be good enough. And how do we prove this? Well, this is just a matter of simple expectations, because all these we can just treat them as random variables. Expectation of a squared is going to be equal to the expectation of the sum over s equal 1 to m of xs fs to the 4th power, right? And this is where the 4 independence requirement comes from. So that's going to be equal to the expectation for the sum from 1 is less than or equal to s, t, u, and v. So we have 4 different variables is less than or equal to m of x sub s, x sub t, x sub u, x sub v, f sub s, f sub t, f sub u, f sub v, right? So we're just expanding out this product. And notice that we're going to make use of notice if any of these are distinct, if any s, t, u, v are distinct. So if any of these have a value, are distinct, then by 4 independence, what is the expectation? So first, what's the expectation of x sub s? Yeah, the expectation of x sub s is 0. So now these are all independent, and so if any one of these variables is distinct, then you can then it is independent, and you can multiply expectations, right? And so if you can multiply expectations, that means that if any of these are distinct, then the expectation is just 0. So you can ignore all of those cases. So that implies that only cases are either all 4 variables the same or 2 pairs, right? So those are the only possibilities. It's like either you have 2 pairs of variables that are actually the same variable, or you have all 4 variables that are the same. So that means we can rewrite this. So then we can rewrite expectation of a squared is going to be less than or equal to 4 choose 2. So you have 2 different pairs of the expectation of the sum from s equal 1 to m times the sum from t equal s plus 1 to m. And clearly those 2 are distinct. X sub s squared, x sub t squared, f sub s squared, f sub t squared, plus the expectation when they're all the same. So that's the sum over s is equal to 1 to m of x sub s to the 4th, f sub s to the 4th. Yep.
Why does this be equal here, or is it?
Oh, yeah, sorry, let's equal there. It's going to be less than or equal to in the next line. So or in 2 lines when we actually, yeah. So So then this is equal to 6 times the sum over s from 1 to m of the sum from t is equal to s plus 1 to m of, well, what's xs squared? Yeah, and x sub t squared is also always 1. So this is just f sub s squared times f sub t squared. And we have the same thing over here. So that's just the sum from s equal 1 to m of f sub s to the fourth. Well, this turns out to be less than or equal to 3 times this summation, s equal 1 to m of f sub s squared squared. So that's pretty easy to verify. Basically, expanded out, it's going to be significant. It's just going to be strictly greater than, and that's equal to 3 times the expectation squared of a, which completes our claim. Okay, and so this is how we're making use of 4 independence, because it turns out that we end up in our analysis having 4 variables that where we want to multiply together all the expectations, and we want them to be independent to make this analysis work out. And so by choosing a 4-wise independent random hash function to begin with, we're allowed to do that in a way that we wouldn't be if we chose lower amounts of independence. And this, of course, allows us to prove the theorem that we care about. This is theorem 6.3. In this proof here is from the Foundations of Data Science textbook. The other proof that we did earlier today is from Jelani Nelson's textbook or lecture notes, which I've linked online. So the theorem here is the average x of r equal 2 over epsilon squared delta estimates a1 through ar using independent sets of 4-way independent hash functions. So basically we're doing this r times. So the standard trick of just scaling, doing it many, many times independently is going to have the probability that x minus the expectation of x is greater than epsilon times the expectation of x is less than the variance of x over epsilon squared expectation squared of x is less than or equal to delta. And I'm not going to go through and work through all the details of this proof because it looks exactly like all the other proofs that we've been doing. And the variance of x is just less than or equal to delta times epsilon squared, the expectation squared of x. And the rest follows by Chebyshev. Okay, so this gives us, so now we have both a, we have a sketch for the 0th frequency moment. We have one for the 2nd frequency moment. And of course, the 1st frequency moment is super easy because it's just the total length of the stream. And it turns out you can continue studying this and develop sketches for higher frequency, for some of the higher frequency moments at least. But that is, I think, beyond the scope of this class. Okay, how much time do I have? I have enough time to introduce the next problem, though not actually go through all of it. So let's move on, unless someone has questions. Okay, great. Yeah.
Briefly go through like the parts where any of the S to UV are distinct and the expectation is zero.
Oh yeah, sure. So since I went through that somewhat quickly. Okay, so let's go back. That was here, right? Yeah. Okay, so let's say I have a number of random variables, right? So if I have 4 random variables, let's call them A, B, C, and D. So if I have A times B times C times D, what is the expectation of lists? Suppose they're all independent.
So it's the product of the.
Yeah, so if they're all independent, then this is expectation of A times expectation of B times expectation of C times expectation of D. But if they're all independent, we know that these things are -1, 1 random variables, right? So each of the expectations of each individual random variable is just 0. Because there's 1/2 probability of being -1 and 1/2 probability of being 1. And so therefore the expected value is 0.
Yeah, that makes sense. I guess I'm more confused though, why are the only cases the left are the ones that
Yeah, okay. So if they're all independent, this is the case. Suppose that 3 of them are, suppose one of them is independent from the other 3. So suppose that A is independent from the other 3. Well, if A is independent from the other 3, then you can rewrite this as expectation of A and expectation of B times C times D, right? But since that one's distinct, that means that that expectation is 0. And so then that's equal to 0, and the entire thing goes to 0. So you can't have exactly one distinct thing. Okay? In fact, you can't have any distinct things. So none of these A, B, C, or D can be distinct from each other. And so what does that mean? That means that whenever you see A, it has to appear at least twice. So for example, expectation of A times B times B, that does work, right? Because that's expectation of A squared times expectation of B squared. And those are equal to 1. And so whenever you have, so long as none of the random variables are distinct, so as long as none of the random variables appear exactly only once, then the contribution of that to the entire sum is well positive. But if you have any distinct random variable, then all of a sudden the entire everything goes wrong, or I mean doesn't go wrong, it just goes to 0. And so you can ignore that. And so here we had the case where you had 2 pairs, because that's one way for nothing to be distinct is to have 2 different pairs, right? And the other way for them to not be distinct is for all 4 of them to be a little same. You can't have 3 of them the same, because if 3 of them the same, then the 4th one would be different. Yep. Okay. Given that explanation, I am actually out of time. Like next time we'll talk about majority and frequent. Oh no, that's fine. Like I was going to have to review this stuff next time anyway. So tomorrow we're going to finish off the section on sketching basically. So tomorrow will be the last day where we're talking about sketching. We're going to talk about the majority and frequent item sketches, as well as talking about the min-hash sketch. And then next week we'll get to move on to random graph theory. So I think I will end there.
We're almost done with sketching.
Yeah, this isn't a class on sketching. This is a class where I'm introducing you to all these kinds of cool techniques. But I'm giving you just enough to whet your appetite, but not giving you enough to be like, wait, I understand this now. That is the point of this class. So, yeah. Okay, bye everyone.